Okay, remember if we have f of x is equal ln, we are going to have the first derivative is 1 over x, right? So if we have f prime 1, this is equal to 1, okay? Now remember that if we have f prime 1, we can write this in terms of limit definition. Right? Let me write the formula here. Okay, so we can take that. Now it's changing to x. Okay, so I'm changing the age, all age to x, and changing x to 1. Okay, so this is also changing to x. Okay, now we can simplify it. Take 1 over x. Forget to write. So limit as x closer to 0, 1 over x, and then ln. So I can write this as just 1 plus x because ln 1 is 0. Okay. And then from this 1 over x, I can replace it here, right, with the logarithmic property. So I can write this limit ln 1 over x like that. And we know that f prime 1, we did the calculations from our derivative is equal 1. So we can equaling this with 1. Okay? Okay, now I would like to start with, if we have e is with the power 1, right? And we can replace this 1 with this. So we can write down that e can be powered by limit and for exponential, this is something that you need to pay attention. For exponential, because it's just a constant, when you have this limit and it has the ln, we can move this limit inside the ln. Okay? That's one of the limit property. So exponential, and then write the or we could write directly outside here, limit. It's the same thing. So we could take this and write down that this is going to be 1 plus x, 1 over x. Okay. So basically what we did here is we just take the e and make this ln as a power. So this will be E, this will be E. So that's why it's equal becomes E when we have E. Okay. So this will be equal to E. So the takeaway from this is you can write your E as limit and another expressions. Let me write with the second expression. This is the first expression. The second expression is if you let the x equal 1 over n. Okay. So when x is closer to 0, then n is closer to infinity. Now you can also write that as limit as n getting larger, 1 plus 1 over n, and then this will be n. Okay, we can also write it with these two expressions. We can rewrite E with the limit as x close to 0, or we can rewrite as, well, you can say n closer to infinity. And you could also try to check the graph this 1 plus x with power of 1 over x. You can try to graph. Let me give you illustration around here. Okay. This. So you could look at this point that has all removable discontinuity here. When we taking x closer to 0, it goes to this point, and this point is actually our E. It's around 2.7. The first one is from here. From there. Oh, okay. So previously we illustrate the number E with some approximation through the a number of ln between 2 and 3, ln 2 and ln 3, right? And then E is resulting 1, ln E is 1, right? And now we get through with this another perspective using the this expression or this expression. This is also the same expressions when you're dealing with the interest in the banking system. They're usually also using the same formulation. So if you have, it is called the compound rate interest. I think I will not go into details. Okay, maybe any questions first? This is just a small notes about the Ln. Okay, so you could also proving this with the Ln property, and getting the number p. You will notice, I think in the next 2 or 3 sections, we are going to see a lot of this part when we deal with the indeterminate forms. So we're still dealing with limits again later in indeterminate forms, the L'Hopital rule, but that's after we deal with this sketching the curve. Before chapter 3, there is 1 more techniques and 2 sections that we need to finish. I hope this okay. Okay, let me go through the next page. Okay. So the next part is the inverse of trigonometric functions. I mean the derivative. Okay, derivative. So let me recall you with some definitions. Okay, if you have the inverse, sine inverse like this, and remember this inverse, it doesn't mean that it's 1 over sine. Okay, please be mindful. This is not the same. Be careful. Okay. We can also write the sine inverse with arc sine x. Okay. You can write with either of this, sine inverse or writing arc sine. I prefer the first one. It's simple and shorter. The meaning of this inverse is that sine y is equal x, right? From this definition. And based on what we know about the inverse, if we want to have an inverse, first we need to prove that the function is 1-to-1 function, right? You remember the chapter 1. So to make this sine of 1-to-1 functions, we need to set the domain and range. So we need to set this y with certain value. Usually we just take minus pi over 2, the default value. So when we set this y between this value, we will have 1-to-1 functions. Okay, since we have learned how to differentiate implicitly, I think the sine y equal x easily to be derived. Right? Sine y become cosine y and then dy over dx equal 1. Okay? Let's write that. So we could write dy over dx is 1 over cosine y. But it's not finished yet. We still have y. Okay. If we want to replace with x, then we need to tell how does this y relate to x. Remember that sine y is equal to x. The easiest way to follow up this is because we are having some certain angle as its domain and range. So it's best to think the inverse of trigonometry inside a triangle. So let's draw a triangle. Why it's become ellipse? Okay. Okay, yeah, let's say that's the angle. So the angle is y, right? Sine y is equal to x. So y will be here, right? And we can write, if you remember the trigonometric, let me write over 1 here to give you easiest way to look at that. This is this side, I would say the opposite side, right? And 1 is, for sine, is the hypotenuse. Okay? So let's just write all of them. So y, this is x, this is 1. So the other side, the adjacent side, will be square root of 1 minus x squared. Right? Now what is our problem? Our problem is cosine y. We need to exchange cosine y with our this from this side. Okay? Cosine is what? This over this, right? Okay. So we could write down. Let me write here. Cosine y is. Let me write over 1 like that. So dy over dx, or dx of, this is actually sine inverse x, is equal 1 over, okay. So most of the inverse of trigonometry, we can prove most of them by using the triangle, this triangle. Okay? And this is really helpful if you sometimes nervous, forget, you can just write the triangle, draw the triangle, and then you can fill out all the terms and matching with your unknown or your question. You can match. And of course, the techniques, like the differentiation techniques, by the end of the day, we are going to have a combinations of all possibilities that we already learned. And this is one of possibilities. So maybe we can have this inverse of trigonometry combined with the log, combined with the chain rule, combined with everything. It could be possible. But one thing to remember is you don't really need to memorize everything. What you need to do is you need to know the process, know the steps, know the process. Perhaps if you are not really familiar, maybe it takes time at the beginning. But what I can give you advice: do some practice, do some exercise. Don't wait for me to give you practice. Okay? You can look on practice everywhere. I will give you practice, but don't wait. Please, you can do directly after you get all the things from the techniques. You can try some exercise, some practice, and perhaps this week, maybe I'm trying to give you some homework. Okay, some homework. Maybe 5 to 6 questions, mostly about the techniques, because this is the last techniques, the inverse of trigonometry, last techniques for chapter 3. Okay. Okay, now if we have, let's say we have the y equal tangent inverse x. Okay, maybe I'm trying to give you sometimes to try and by yourself. Right? Similar method. Try implicit differentiation. You get some terms. You need to put back into the triangle and exchange the terms back to the x terms. I try for maybe a couple minutes. I think not too difficult. Not too difficult. We can start with taking tangent y become x. Tangent y equal x, and then differentiate. You get something, and then exchange all the y terms with x. You need to find the cosine y in terms of x. I think some of you already familiar, right? Already discussed with. Okay, so we could start with tangent y is equal x. Take derivative. Implicit. We take this as this, and we are getting our dy over dx is 1 over secant squared y, or this is cosine squared y. So we are going to be to write all the terms. So this is y. Now tangent is x and 1 here, right? So we are going to have square root of 1 plus x squared here, right? So then we will have the cosine is 1 over square root of this 1 plus x squared and then square root of them. So that's why it's become 1 over 1 plus x squared. So this will be d dx of the tangent inverse x. Okay. Now let me give you some summarize everything for the inverse. My suggestions, I think you could just take some formulations like the tangent inverse is very popular. It's frequently shows up. I think the first three, this part, very important. This first three, at least this first three will be appears quite often. The most frequent is the tangent inverse, because the form when we derive is quite common. We can see this 1 over 1 plus x squared. Every time we see any rational functions, like regular rational functions, we are going to see maybe we could take some extract that in this form from those rational functions, and it will be very useful later. Okay, if you want to take photo, maybe let me put closer here. Okay, if you want to take picture, it's bigger. Okay, in your textbook, we still in the, this is I think 3.6, but I would like to skip some parts. If you have maybe access to your textbook, I will skip 3.7 and 3.8. So that is about the rate of change, growth rate, populations, some modeling. I will skip all of that, and we directly go to 3.9. 3.9, which is related rate. It's called the related rate. We are going to review and give you maybe some practice, perhaps tomorrow. Okay? We can review all techniques and maybe some combinations. But let me go through for today with the next section. Okay. Okay. Okay, I hope you finish all the notes. So the next is the related rates. So what is related rates? Related rates is usually this is a problem when you have some phenomenon, like something is changing, maybe some rate, maybe when you move, maybe if someone moves, okay, maybe he's moving here and moving there, and you are in the middle, maybe also move. You will have some different perspective on how fast the other one compare with you. You will see some differences. It's like, if you remember learning like relativity in physics, you see some different perspective, different angle, and different conclusions. Right? This is similar, but not that complex. Actually, not that complex. Okay? So, for example, if you have maybe this person goes here. This is person A with some speed, dA over dt, and this is B. This is with also some speed, okay, with also some velocity, and we know the time, and then we know the how fast A and B. We could imagine that how fast this A and B will meet at this intersection. Okay, this kind of question. One way to get through is to imagine that this is like a triangle, and when A moves, it's the distance getting closer, right? The distance is getting closer to this point. Also B is distance also getting closer. But what kind of formulations that we can get through the AB? If we see this as a triangle, we could take this as a triangle. Okay? Like for example, the triangle. Let's say this is. Let's say this is side C. When A moves and B moves, C also getting smaller, right? C is getting smaller. So if we can formulate this into our triangle formulations, or the using hypotenuse here. So C is maybe A and B. Okay. So A squared plus B squared is equal to C squared. Okay. And all is respecting to the rate of change with time, right? With time. So the variable is the one that change is time. So we could take derivatives. We could take derivatives with respect to t. And simply we are going to implicitly derive. So perhaps this is going to be, let me just write with 2a and then dA over dt. Or maybe this is maybe A is more clear, and B. And plus 2b dB over dt, and then 2c dC over dt. So if we know some part of it, we are going to, maybe the question is asking the C, and maybe you are given the information about the speed, the velocity, and you can find C, okay, or you can find the dC over dt. How fast they are going to meet is dC over dt, and how the distance is 2c, the initial distance. So this is one kind of example. So you will see more of the rate of change phenomenon, okay? And in that rate of change phenomenon, you will see how to relate one terms with another. How to relate them, usually with some familiar formulations. Like this formulation is quite familiar, right? And the problem is, I think most problem will be simplified, so you don't really need to overthink of some problem. Okay. Let me give you another perspective. I will just get through all the examples. And because most of the problems, they are written in a long paragraph, you need to take time to understand the problem. And I believe most of the problem in your textbook, it just came up this like a long paragraph. So I will try my best to provide you at least with clue and hint what to do. Because if not, I believe most of you will be confused how to deal with this. But I think for the example in your textbook, there are 5 examples and they are quite easy to follow, I think, for example. But for the exercise in your textbook, usually they just give you the long paragraph, maybe not giving you any clue. Some of them maybe giving you the diagram, the structure, like the illustration to understand the process. Okay, now look at the question. The air is being pumped, okay, into a balloon. So you have a balloon, you are pumping the balloon, and the volume is increased. Okay. So whenever you heard something is increased, it means that there will be something change. So there will be. So if this is a volume, and volume is usually V, this will be having dV over dt. Okay, something change. How fast is the radius of the balloon increase when the diameter is 50 centimeters? I hope you understand the question. It's asking the radius is changing. So the volume is changing, the radius is changing. So perhaps we are going to see the volume formulations for the sphere, for the balloon. I hope you know what is the formula. Okay. So maybe I will write the balloon, okay. So this is the initial conditions. It has some R, right? And it increase with some R plus, let's say, dr, or maybe let me just write with some terms. This is R1, this is R2, and we have the dV over dt is 100. It's asking how fast is the radius, so dr over dt is asking, or perhaps this is clear. So dr over dt at diameter equal 50 centimeter. Okay, that's how to imagine the questions. Or maybe you can write the d as r. So r is 25. So to connect dv over dt and dr over dt, we could first write down the formulations. 4 over 3 pi r cubed. Okay, this is the sphere volume. Okay, now, as usual, we are going to differentiate with respect to t, and we are going to have dv over dt is 4 over 3 multiplied with 3 pi r squared. So dr over dt, sorry. So dv over dt is 4 pi r squared dr over dt. And then we can take all the information inside. This is 100. This is 4 pi. R is 25. And dr over dt. So we could have the dr over dt. This will be 25 and 25 will be there. And then we have, this is 1 over 25 pi centimeter per second. Okay, one example. Okay, so this is how we correlate some terms in some rate of change with another rate of change that is in one phenomenon. Okay, we will have a break, okay, and we'll continue after the break. Okay, the next one, I give you this example 2. Example 2, you have a ladder. So let me just give you this and see if you understand what the question means or what the problem is. So a ladder with some certain long 10 feet rests against a wall. So it means that you put your ladder, you put it here. If the bottom of the ladder slides away from the wall, so the ladder it slides away. It tends to move that way, away from the wall, and it has some rate 4 feet per second. How fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? So this is so what the question asks? Okay. So if you have a ladder, it slides away. So this bottom part you have some fixed rate 4 feet per second. But how about this vertical side? How fast it is? How fast? So to know how fast it is, we need to maybe first we take some time to draw. Okay, draw the diagram. Let's draw maybe here. Let's say this is the wall, and this is the ladder. And this is the ground. Okay, this is 10 feet. And then it doesn't give you any symbols, any variables. So we name our variables by ourselves. Okay? Maybe naming this is y, this is x, because it's easy to follow. Y is the vertical, x is the horizontal one. And then it's give you the 4 feet per second. So it has dx over dt, 4 feet per second. Let's say the 4 feet per second, because it slides away from the wall. Remember that every rate of change or every that has change in directions, it will change the value, at least for the signs, positive, negative. Okay. Please take notice on yourself that you need to be consistent. Sometimes it doesn't really matter what signs you choose. As long as you're consistent, the result will be same conclusion. If you take, for example, you take this 4 feet per second as positive, meaning when you take away this ladder, you're telling that, okay, I will make this as a positive sign. That's okay. If you take this as negative, that's also okay. When you have the result and result is negative, then maybe it's the same way with this. But if we have this goes away here, then this should be goes away here, which maybe there will be something different from what we have. So this is similar approach with the previous example. So we are going to have the triangle. X, Y, and 10. So we know that this will follow these formulations. X squared plus Y squared equal 100. Okay. Now, as usual, to get the rate, we are going to differentiate with respect of t. Okay. So we are going to have 2x dx dt plus 2y dy dt equal to 0. And we are going to have some relations. So 2x dx over dt is equal, or maybe we can cancel this 2, is equal negative y dy over dt, or we could write dy over dt is equal negative x over y dx over dt. Okay. Okay. Now we have dx over dt, right? This one. And how about x and y? We also have, in the last sentence, it says that we need to evaluate dy over dt when the bottom of the ladder, this x, is 6 feet. Okay. So we are not sure how will be the ladder. Is it like this, like this? So we are not sure about initial x, but for sure the question is asked when x is equal 6. Okay. So we are going to look at this triangle, and if this is 6, then this is a perfectly Pythagorean triangle. So this will be 8, right? Okay. So we get all y and x. Okay. So the conclusions, we are going to write down that dy over dt, that's the questions, is negative 6 over 8 multiply with 4. So we have the negative 3 feet per second. So remember, what does negative means in our definitions from the previous one? You may have different value, but to understand what this value means is, if we say that when we have this positive, let's say it's defined that the distance is getting larger. Let's say that because it's easy to visualize, it's getting larger, so maybe this is positive. Okay. And this getting smaller, so maybe it's getting negative. Okay. But I think from what we have here, it's easy to say that when it is going to here, this is getting here, which is the opposite side of this, right? Okay. So it's perfectly okay. So we say that this negative means that the ladder is getting dropped, okay, and the distance, the vertical distance, is getting smaller. We could say that. If you take, for example, if you take this to be negative, your result is positive, but with same definitions, it's also okay. It depends on you. As long as your definition is consistent from the beginning through the end, you will get the same result, same conclusion. Okay, and the ladder problem is, I think, one of the most typical problem in the related rates. Okay? So let me give you some notes around here. Okay, what you need to what you need to do. First, okay, understand the problem. Two, draw diagram or illustration. 3, naming the variables. 4, express the rate. 5, find formulation. Differentiate with dt. Substitute the information. Okay. But I think this is quite intuitive. Okay. Of course, you need to understand the problem, what you need to find, what is your goal. Drawing the diagram really help. Okay. So that is really very the best suggestions. Draw diagram. And then naming the variables, like we did before, we name x, y. You can name it the different variables like a, b with anything. Okay. Express the rate, which means that which one is the one that you the one that is being asked, or maybe some information in the questions, name that or express all the rate. That is possible. And find formulations, how to connect all the phenomenon, all the related rate phenomena, all the rate phenomena inside. Connect all, and then differentiate. Why we need to differentiate? Because we need to express the rate. We need to express the rate within the formula. And then you find the information, substitute, and we find our goal. So it's actually, the task is quite simple. The problem is how to understand the problem and how to connect with the formula. That's mostly the problem. Okay. Yes. Yes. Related rates. Yeah, it's okay. That's the same problem. A different edition, but the same problem. Don't worry about numbers and everything. As long as you understand the concept, should be okay. Sometimes some edition use the feet. I think this is for American standard. So sometimes using the centimeter, meter, but anyway should be the same concept, the same formula. Okay, now let's get through for another example. Okay, again, we need to do some readings. So perhaps if you're not familiar with some terms, I will help you with that. And perhaps also, when I give you some practice or exercise, maybe I will also give some hint and maybe some picture to illustrate what the question actually is. So a water tank. So you have a storage for water. It has the shape of inverted circular cone. So it is a circular cone, but it's inverted. So you could imagine like cone, but inverted. It has radius. The base is 2 meters. The height is 4. And then water is being pumped with some rate, 2 meters cubed per minute. Find the rate at which the water level is rising when the water is 3 meters deep. So maybe before we think what is this, draw all the possibilities. Draw the tank, and then maybe some illustration of water going inside. And you see that it has some rate, it has some height for the circular cone, base radius, we have also the 2 meter. And then the water is filled up the tank with this height, this 3 meter. Okay. So let's draw all that stuff. Okay, let's say this is the water tank. The base is this. The radius is 2 meter. And then we have the height. This is 4 meter. And there is a water, let's say water here. And it's maybe filling the tank, maybe here. Okay. One tips for you. If it's already being said that it's asking when the level of water is 3 meters, do not write 3 here yet. And do not yet write that, because you will be confused on what your goal is. Like the previous one, okay? Let me go back for a while. The ladder part is the same thing. You need to find the rate when the bottom is 6 feet. Do not write 6 yet, because if you write this, you have a fixed, a constant. Okay, you have a constant, and when you deal with this, you will find, oh, what did I miss? So write this as x, because it's changing. Okay, because it's changing. You can plug the 6 later at the end of the conclusion. Okay? So same thing here. Do not write 3, because this water is not a constant. Okay, it's not a constant. It's changing, right? So write with something else. So write with let's name the variables. Okay. Okay, let's say we are having the let me write maybe different color. Let me write it green. Let's say we have, this is R, okay, and this will be, let's say H for height. Okay, maybe it's easy to follow. So let's say this is H. Or maybe let me write here, h. Okay, now next thing, so we draw all of this. The question is asking the level, water level. So it's asking the level of the water, the rate, the change. So we say it's asking the h over dt, because I take this h as our names. So the question is asking about the h over dt. And we know that the rate of water is 2 meter cubes. Okay? So it's pumped from somewhere else. So the rate of water, let's say the water, because the water will fill up the cone, and let's say the cone is one big volume. So let's say it's dv over dt. Okay, let's just name dv over dt here. It's 2 meter cube. Oh, minutes, sorry. Okay. Now the best way to connect all of this, I think we go through the volume of the cone. I hope you're still familiar with the volume. So volume of the cone is 1 over 3 pi r squared and h. So the area multiplied with the height. Every volume, you have area multiplied with height, right? Okay. Now we have volume 1 over 3 pi r squared h. So now, after we get this formulations, and we need to make sure that all the details is already written. So let's take the implicit with respect to t. So take the implicit, so we will have dv over dt this will be 1 over 3. But I think we have a problem here. We have a problem. We have r and also we have h, which both of them are changing. So when we deal with this, we are having dr dt and dh dt. So maybe we need to simplify this first. So how to simplify it and how to make it into just one variable. So if we look here, we have 4 meters here, we have 2 meters here, we have h, we have r. So let me draw a triangle here. So this is 4, this is 2. Okay. So I can write r over h equal to 2 over 4. Okay, with the triangle equivalency. If you still remember that. Or we could write r is half of h. Or h is 2r, okay. So the best way, I think, because it's asking dh over dt, if we change the r with h over 2, we are going to have the variable is just h for the right equation here, which we are going to evaluate, and we can get the dh over dt directly. Right? Well, you could also maybe write with R, but you need to do another process to bring back the dh over dt, to find the dh over dt. Right? Because if you have R, then you have the R over dt. It's not the question asked. Right? Okay. So we take maybe changing first the v. This is h squared over 4. So h cubed over 4, right? Or v is pi over 12. And then we take the derivative. So this will be 4 pi over 4 h squared and then dh over dt. Okay, dv over dt is 2. This is pi over 4. H is asking when h is 3. Now we can plug in this 3. Okay, we can plug in this 3. So 3 squared and then dh over dt. It's 9, 8. So dh over dt is 8 over 9 pi. Is it centimeter or meter? Meter per minute. So every related rate problem is always telling you there will be some rates that are connecting to another rate. What you need to do is find the connection, find the formulation, and then do some implicit. And you need to make sure all the components in this implicit is already given in the information. If not, then you need to find a way to find this information also. Like for example, this one. At the beginning, we have r squared and h. If we just take this implicitly, we have two variables that still need to simplify. Like this dr over dt and dh over dt. One way to simplify it, maybe we having this and this connection. Okay. So I think this is also needs some experience. You're just given the questions, like plainly, just the questions. Maybe it will be difficult. So perhaps I'm trying to give you not just questions, but maybe pictures or some clue, like which formula you need to take. And hopefully some terms, the English terms in the questions, hopefully you can be more familiar with that. I think all the examples in the textbook, it covers most of the problems, most of the variants in this chapter. Okay. Let me give you another example. Okay, another example. Perhaps if you're looking at if you have the textbook, maybe different number, but that's okay. It's same problem but different number and different units. So this is a car. We have two cars that is traveling and supposed to be meet at some point, and it's asking at what rate are the cars approaching each other when car A is 0.3, car B is 0.4. So it's not asking the rate of one of them, but it's asking the rate when both of them meet when they have this distance. So it's like the previous one that I explained to you. It's kind of like relativity. So you have a third party that looking from somewhere else and how fast that they meet. Okay, first thing, maybe drawing some pictures like car is going traveling west. So A is traveling west, maybe west is here, okay. And B is traveling north, maybe here. They meet at this cross section. And you can denote the distance with some symbols, but I think you can just name it as A and B, and then you have dA, dt, and dB, dt for each velocity.
Maybe let me draw it to give you more clear idea what happens. So let's say this is the car. Let's move out here. So let's say it's moving. So let's say this is A. And another one, let's say this is the car. This is B. Okay. And it's going to, let's say maybe point C at this point. Okay. Yeah, let's naming the distance is A and the rate, the dt, is 50 miles per hour, and dB dt is 60 miles per hour. And again, because it has direction, you can choose what is your rule for the sign. For me, well, I can choose positive, okay, but it's getting smaller in distance, right? So for me, I prefer negative, just to make sure I am consistent on this smaller and increasing part. But you can check with positive signs. I will take this as negative. Okay. Now,
to make it true, imagine this A is moving here, B is moving here. The question is at what rate the cars approaching each other. So we need to have another perspective. So not A, not B. So perhaps we need to find some way to connect these two. So maybe we take distance between this AB at the beginning, at the initial, and we also see that when this hypotenuse
when AB is moving, the hypotenuse also moving and also getting smaller, right?
So we could take that as our, let's say we are taking this, okay. Okay, maybe this is not C, maybe another point. So let's say this is C to make it easy to follow. So ABC, so A, B, C, like that. So we can connect all this ABC with the Pythagorean A squared plus B squared equal C squared. Okay, and then we can take this, take derivative. So we are going to have 2A dA dt, and then plus 2B and then canceling all two. So we are going to have dc dt is equal 1 over c multiply with the a dA dt plus b dB dt. Okay. I think we can let this dc dt, as the rate that in third perspective that observe A and B getting closer together. Okay. So what we are going to do next is we need to find C and then plug in A and then the velocity and B and its velocity. And I think for AB, not a problem. So for C, I think we can just go to the Pythagorean one more time. So we take Pythagorean. And it says that car A is 0.3 mils. This is 0.4. So the hypotenuse will be 0.5, right? Because of the Pythagorean. So we are going to have dc dt is 1 over 0.5. A is 0.3. And then negative 50. And plus 0.4 negative, what is dB dt? 60. I think you can just calculate this. This is around negative 78 miles per hour. And remember, the sign is not really a problem. You can have positive also, but you need to make sure the definition. Okay? Because I take the definition for negative to be smaller and smaller. So this is also the same thing or the same definition that is smaller. So the C is getting smaller, right? Okay. When AB going to meet, the C is getting smaller, maybe here. Okay, this is C, right? So again, in the related rates, I think do not overthink it. Like maybe you pinpoint some other factor, something else, and then put inside. It will be
very difficult to solve. Be careful. Okay. If you take the signs to be positive, then you will have the positive as the result, and I think it's still okay because it's consistent. It's consistent. Okay, it's supposed to be one example left, but I think that will be tomorrow. Okay, so I will stop until here, and we're going to have a feedback as usual. Okay. Any questions first? Any questions? Okay. Okay, we will have more exercise tomorrow and continue this part. One more example. I think I prepared questions about the derivative of log, I think, and the other one I forgot which one. Okay, I think we can start. Okay, I think we can start. Okay. Okay, use your ID number. Okay, we are going to start right now. Oh yeah, one is implicit. All the options, if you plug in the point, will be the same. So you need to find the tangent line first. The slope. I think you need to find the slope first. I hope the time is okay, around 3 minutes. And now it's already 2 minutes out. Already 3 students submit very fast. Okay. Around 1 minute out. I think because you already have options, one way to think is find the slope and you will get the answer back.
Okay, very good, very good. Okay, very good, very good. Okay, next one. Last questions. Okay, around 3 minutes to 50. I think I will also explain tomorrow for this one and review for some parts of the techniques. So you could derive directly or separate with ln. Yeah, it's supposed to be the. I'll explain later. Tomorrow. Okay, tomorrow. Let's see. Okay. Who is nine? Oh, okay. Okay, good, good. Okay, just some notes and some feedback from you about the quiz. If you have anything to say, like maybe suggestions after this part, you can write. But I need to know how we scale for the quiz. I think for the time is okay, right? For quiz time is okay.
Teacher, I found that if you refresh the page, the tiny bit will reset.
Yeah.
Yeah, and I accidentally refreshed the page.
But does the anything
I think if I refresh the page, then sometimes the answer that I already fill in, it will change to blank.
Oh yeah.
And I think I accidentally just submitted.
Oh.
I forgot to check if.
Maybe I'll write some notes. If you refresh it, you do this inferior answer, right?
Yeah.
Okay. Okay. Okay,
One more. Your ID and feedback, anything, maybe quiz, TA. Okay. I'm planning to give you homework maybe by this weekend. If you finish, then see you tomorrow.